Okay, guys, moving on. Well, I only got 12 minutes. Energy. So the big idea in energy is that energy is this very vague, abstract idea. We kind of call it the accounting system of the universe. But we talked about work, and so we'll start there. We can define work as the transfer of energy. So work is the transfer of energy from one form to another. You have to have a force to transfer the energy. You can't transfer energy from one form to another without a force. And the amount of energy you transfer is the force times the distance over which that force is applied, but they have to be going in the same direction. So to account for that, we throw a little cosine of theta in here. There's two special conditions you need to know. You need to know that if theta happens to be 0, then the work just equals the force times the distance. And if theta happens to be 180 degrees, the work is minus the force times the distance, because the cosine of 180 is -1. That comes into play when you have a problem where you have something sliding across the ground. It's moving this way, but friction's acting that way. And so the work done by friction is negative. It removes energy from the system. Okay? This is also one of the problems where you have to know how to read a graph. If the force is variable, if it's not constant, then the way you find the work is the area under the graph, right? So the work, the energy transfer, is the area under the graph if the force is variable, it's changing. So if the force versus time graph is given to you, the area is going to tell you if it's force versus time, the area is the impulse, the change in momentum. If it's force versus distance, the area is the work, the energy transfer. There are a couple of equations, forms of energy you have to know. Kinetic energy, of course, is 1/2 mv squared. Potential energy due to gravity is mg times delta h. It's always delta because it's the change in height, because it's always relative to a reference point. And for a spring, the potential energy, elastic potential energy, was 1/2 k times delta x squared. Okay? The big idea for this equation, for this unit, was this. The mechanical energy of a system at the end of a process is equal to the mechanical energy at the beginning of the process plus any energy you transferred in and out. So the big question you're going to have to ask is, when you're solving a problem, is energy conserved or is momentum? How do I decide? What's your rule of thumb? What's your heuristic? What are you going to do? How do you decide? Am I going to use energy or am I going to use momentum? Or is there one object or is there a system of objects? If there's one object, in general, you're going to use energy. You're going to analyze the energy of that object. A cart rolling down a ramp. A ball on a compressed spring pops up into the air. Those kinds of problems will involve one object. You're generally going to look at energy. If you have two objects interacting, a bullet hits a block of wood and they swing off or they fly off the table or something, you're going to use momentum for collisions. All right? So that was that problem. The most common problem we see, and this is, just basically all kinds of things where they have cars rolling down, balls rolling down ramps and then becoming projectiles and stuff like that. Energy is conserved in that case. All right, circular motion. There's a difference between circular motion and rotational motion. Rotational motion is when a solid object rotates. Circular motion is when a point object moves in a circle. Okay? So for circular motion, you have an object moving in a circle. Some things you got to know about it. First of all, the force on it to make it move in a circle has got to act towards the center of the circle. That's called the centripetal force. And which way is the acceleration of an object moving in a circle? Towards the center. So what you have to know is that even though the velocity at this instant is that way, the force is moving towards the center. The force required to make something move in a circle is mv squared over r. or the acceleration of the object moving in a circle is v squared over r. This is the one on your reference sheet. If you combine it with Newton's law, you take an acceleration and multiply it by a mass, you get the force. Okay? Later on, we'll talk about circular rotational motion, but there's a relationship. You guys might remember that omega, the angular velocity, times the radius equals the linear velocity. You guys remember that? If you stick that in here, you can write the centripetal force in a different form. It's m omega squared r squared over r, which just gives m omega squared r. Sometimes it's handy to be able to find the circular centripetal force in terms of omega. You don't have to, that's just sometimes handy. Okay, all right, so that's circular motion. And then gravity, of course, our old friend. The force due to gravity equals some constant, which you have on the other side of your page, right, in the fundamental constant section, times mass of object 1 times mass of object 2 divided by the distance between them squared. This is an inverse square law, so you'll see conceptual questions about what happens if, 50 kilograms and 50 kilograms of apples. If half the apples get shifted to the other barrel, what happens to the force of gravity? Well, instead of 50 times 50, you're going to have 75 times 25. Just work it out. Or what? We sometimes call this part of our equation right here the local acceleration due to gravity, little g. So little g is big G, the mass of the planet divided by the radius squared, right? And then if you can then write the force of gravity equals this little g times m, which is exactly what we had over here, F equals mg, when you're on the surface of the Earth. So the thing to remember is F equals mg, finding the weight of an object, is only valid on the surface of the planet. Anywhere else, you've got to use the more general form. Also, if you're near a large object, so here's the big Earth, and here's the little u right here, and you want to know how much energy do you got to pay back to get free of the Earth, to be gone. You got to find your potential energy. Not your relative potential energy, which is mgh. That's how much energy I have right now compared to the floor. But how much energy do I need to add to get me off this Earth? You got to know that the potential energy due to a gravitational field is g m1 m2 divided by r. And that's on your reference sheet at the bottom. And I'm missing one thing that's really important. What is it? Negative. It's negative. Your potential energy in a gravitational field is always negative because you are trapped, you are bound, you're in debt. You got to pay energy back to get free, right? Okay, so that's gravity. Just remember, it's not on there, but the density of a planet equals the mass divided by the volume, which is in general the mass divided by 4/3 pi r cubed. So if you double the radius of a planet and don't change anything else, what does that do to its density? You double the radius of a planet and don't change anything else.
I have a question.
Answer mine first.
I wasn't listening to this.
If I double the radius of a planet, if you take Earth and you double the radius with the same amount of matter, what'll be the density? It'll be 1/8. Because the density goes like r cubed. And the reason you need that is there's some tricky problems on there. So for those of you who are going to get 5s, they're going to say a planet has the same mass as Earth, but half the density. What is g on that planet? And you're going to have to use the relationships to work out g. Okay? So if it has the same density, that means rho is the same. If it has the same mass, you keep mass the same and work out the other things. Okay? All right, the big application of this, I gotta go. Ask me. The big application of all this was what? Orbital motion. So orbital motion was the idea that if you have a satellite orbiting, it's moving in a circle, what direction is the force on the satellite? Towards the center. What direction is the velocity? It's tangential. The velocity is going this way. The force is going that way. How much work does that force do? Well, work is force times distance times cosine of theta. What's theta? What's the angle between the force and the distance it's moving? 90. Cosine of 90 is 0. Centripetal forces do no work. The big idea here was that the force due to gravity is what is making it move in a circle. That allows you to work out G mass 1, mass 2 over r squared, where r is the radius of the orbit. That equals m2 v squared over r. That allows you to find the orbital velocity, and then the orbital period, t. This is the orbital period. The orbital period can be found by using the distance it's got to go, which is 1 time around. So 1 lap is 2 pi r. That equals the velocity times the time, the orbital period. So using that idea and the velocity, which you can solve for here, you can work out the orbital period. Okay?
Sorry for the interruption.
All right.
All AP environmental students, remember you eat a lunch, and then after a lunch, report to the library. You will need pencils, a pen,
Emily, go.
and any scratch paper.
Jump on the
No
line.
phones or smartwatches will be allowed in the library. So AP environmental students report to a lunch, and then the library after lunch.
Okay, so that is the big summary of everything we've done in the fall up till Christmas. Tomorrow, I see you again before the exam, and I'll review rotational motion, springs, sound, and waves.
What's our exam?
Tomorrow.
Wait, what?
Tomorrow is your exam. You go to a lunch, and then you go to the media center.
Wait, what?
You can. I'm not allowed the exam room.
Mr. Black, so it's tomorrow?
Oh, you want a selfie? I'll take a picture with you.
It's tomorrow in the library.
So if you just like spawned a planet in the middle of